Welcome to our webinar. Today we are hosting Chas Meyer from Medtronic, and we are going to talk about how Medtronic secures, monitor, and debugs critical devices. I am Lian Granot. I am the co-founder and CTO of Sternum. I have an extensive background in cybersecurity, embedded development, and Android development.
And I'm Chas Meyer, and as Lian said, I'm the senior principal product and security engineer at Medtronic, and I've worked in embedded systems for 40 years, and recently switched into the cybersecurity team, and I look forward to this presentation.
Thank you, Chas. Let's get started. First, we'll do a brief overview of the Sternum platform. The platform has three main layers. The first layer is runtime self-protection embedded in the edge devices themselves. It's an agentless solution which basically works by embedding verification points throughout the firmware automatically. Then, when the device executes, normally it will self-validate itself, same like a RASP concept. The security itself is deterministic and autonomous, does not require any internet connection. The next layer in the Sternum platform is the observability and continuous monitoring. In addition to the data collected from our runtime protection, you can use our SDK to collect any custom data that you would like from the device. Using this data, we provide you two things. First thing is fleet-wide and also device drill-down analytics. You can see how your entire fleet behaves if you have major errors throughout your fleet, or if a specific device is malfunctioning, and you can investigate that to understand why. Using the Sternum anomaly detection engine, you can get alerted on issues before you get complaints from the field. You can get alerted on a specific device that's starting to behave differently and fix the issue before it affects many devices in your fleet. In addition to that, the observability platform also provides an additional security layer, an XDR-like platform that alerts you if a security anomaly also occurs, not only performance and diagnostics. The first layer in the Sternum platform is the operational and business insights. When you collect data from devices, especially if your fleet is huge and you collect a lot of data, it's very hard to get actionable insights. And this is why Sternum Business Insights allow you to do so without any effort. We know what business insights are relevant to manufacturers, and our platform will automatically allow you to gain those insights. For example, you can automatically understand your battery level throughout the fleet to do a predictive maintenance in case of a battery malfunction. You can see the quality or stability of the devices in fleet to understand if you need to invest more R&D resources in improving your devices. And you can get many more insights using the Sternum platform. Today, we are going to cover some of those insights. So now we are going to talk about some use cases that our observability and runtime security allow you to gain, basically. Chad, do you want to maybe do a quick overview of that?
Sure. After a year of collecting data in the field on one of our products, we took a look at the errors that are logged by the firmware. And when we log an error, it's not always an error. Sometimes it's like if you use a Bluetooth stack API and the Bluetooth connection was lost, you might get an error indication back from the stack. So we log that as an error. So it doesn't necessarily mean these are all firmware errors, but they are just non-optimal behaviors in the system. And so when we collected up this data for one of our products, we found a lot more error logging than we had expected. And it turns out that there were two error sources that were responsible for the vast majority of the logging. And when we looked at the code, we found that it was just a design mismatch in the intent of the error logging, where when you go to schedule an event for delayed execution, you can come around and cancel that event if you decide that you don't want it to execute. And oftentimes that canceling can be performed on a function that's no longer scheduled. And we log that as an error, even though it's normal operation in most of the cases, because we wanted to catch the cases where if we went to cancel it and it wasn't there, we would know. But it turns out that we were over-reporting that particular use case in the error logging. So once you boil away the overhead like that, we drilled down into what the remaining error reports were, and then we used that for going and taking a look at the source code and seeing if these were actual bugs and how to resolve them.
So how did you do error monitoring before Sternum?
Well, that's a really good question because it's incredibly difficult in an embedded system to get observability even during development. Because if you're logging these errors, who looks at the logs? Where are those logs? How accessible are they? And unless you have a really good logging system built out, you're going to have things happening that you just don't know about. And until we integrated Sternum into our system, we would go through the development process and the formal testing without this kind of visibility. So it's possible then to have escapes for some of these bugs into the field. And by integrating Sternum into our product, we can see in near real time what kinds of things are happening so that prior to release, we can take corrective action.
So I have another question for you following that. So maybe it's more of a statement because I think we met many embedded developers from many industries. Some of them had some kind of we say error monitoring, but from what we saw, it's a lot of effort just collecting the errors, but then to actually do the analytics on them and to investigate them, that requires like a very complicated analytic system that no one can actually put the effort into, right? That's like a new product.
Yep. And oftentimes in the embedded world, you have a very targeted set of skills to embedded systems and the C language, embedded firmware programming, and doing full stack development across the cloud to a back end where this data can be collected and analyzed is usually a capability that is just not available within a company. And if it is available, it takes a fair amount of time and effort and staff to build it out and maintain it. So having a drop-in product that's ready to go right from the beginning that gets us to the ability to observe this data without having to develop the capability ourselves is really a godsend.
Yeah, definitely. Do you think devices that has, I would say, rare connection to the internet still need some kind of a monitoring?
Absolutely. There's all sorts of things about the environment that you're operating in and the nature of that connection and the quality of that connection that you need to know how the system is performing in the field, and that's about the only way to get it.
Yeah. Especially, I think when one of your most I would say important causes is to provide your customer or patients the best service they can get. Right.
Yep. All this information helps us with improving product reliability and quality so that our customers have a better experience with it.
I imagine a day where like you have support for PCs or for basically any personal computer, where can someone guide you through the phone and then see what's happening in the system in live. Like you can have that capability maybe in the future for critical devices like medical devices, like seeing telemetry from the implant and from other critical equipment and helping solving issues remotely, completely remotely in runtime. So let's talk about Bluetooth.
Yeah, that's my favorite topic. I've been working on Bluetooth for over 10 years now, and it's very interesting to me how you can go through development and not have exposure to the kinds of environments that you run into in the field. And you really can't know what those environments are going to be like until you do field it. And then getting data back on how it's actually performing is invaluable for refining what you do during development to stress test your system. So we collected up a lot of Bluetooth data that we'll probably be talking about later on how we were able to analyze use conditions in the field.
Okay.
Yep. Now here, I don't know how familiar the audience is with Bluetooth, but we're using Bluetooth Classic, a serial port profile to communicate between our instruments and an iPad. And Bluetooth has 79 channels that it uses, that it hops between, that spread across the same spectrum that's used for Wi-Fi. And so those channels can be adaptively mapped out if there's too much interference in that particular slice of the frequency band. And so one measure of quality of your Bluetooth connection is how many channels are usable. And Bluetooth has an algorithm for mapping in and out channels to adapt to the noise in the environment. And you can read that channel map from the Bluetooth hardware and see which channels are actually in use. And so what we've done is we've taken snapshots of the channel map every 30 seconds so that we have a historic map of how it's performing in that environment. And you see here, this was taken from lab data where we were in an anechoic chamber injecting noise on Wi-Fi channels 1 and 11, with channel 6 being untouched. What you can see there is that on the left of the Bluetooth channel map there, that corresponds to Wi-Fi channel 1. And you can see that most of those channels are disabled most of the time. You can see some spikes there on the backdrop. That's a sum of all the number of occasions where that Bluetooth channel was enabled. And those spikes are the Bluetooth chip periodically probing that channel to see if it's usable yet. It doesn't mean it's actually usable. It just means that the chip is seeing if it's recoverable yet or not. And so you can see on the Wi-Fi channel 1 is interfering with a broad range of Bluetooth channels. Same thing on the right-hand side with Wi-Fi channel 11. And in the middle, we see the spectrum allocated to Wi-Fi channel 6, where we didn't introduce any noise. But one of the odd findings here is why is there a notch in the middle of that spectrum where we're unable to use those channels in that small notch? You can see on the right-hand side there where I've circled that area on the plot. There are 6 Bluetooth channels in there that are just mapped out, and it's in a usable area of the spectrum. So this is an unexpected finding. By the time you have this much interference in a system, losing 6 channels is a big deal. So we would like to know what's going on with those 6 channels, and we'll likely be reaching out to the manufacturer of this Bluetooth chip to see if they can help us understand what might be going on here.
That's great. So how can you actually detect it without, like, what's the traditional way to inspect such issues, let's say, without remote observability?
Well, traditionally, you can get this kind of information if you have like a protocol analyzer, but that doesn't help you with fielded products. We've had reports of Bluetooth interference issues at some sites where it has a significant noticeable impact on the performance of the system. So we'll send a team out there to go and take a look at what's happening, and we'll bring protocol analyzers and instrumented equipment, and we'll take a look at what's going on, and we see nothing. And the problem is that these environments, the noise is changing over time. Like for example, I would expect that Wi-Fi utilization in a hospital would probably peak around lunchtime because people are taking lunch breaks and surfing the web. And if you're using a Bluetooth system during that time, you would get a different pattern of interference in the Bluetooth channels than say at closing time when everybody goes home and nobody's using Wi-Fi. So when you show up to look at this stuff matters, And by having this kind of data collected from the field, we can take a look at what the real operating conditions were at the time whenever a problem does show up, and not worry about sending a team out there to hopefully be able to catch it. It's like remote debugging. I kind of like to think of it as spying on the Wi-Fi environment or on the noise environment for Bluetooth.
With much less equipment, I guess.
Yep, it's built into the equipment we already have.
Yeah, that's amazing. Actually, leveraging that very simple metric, maybe the amount of available channels, to actually detect such detailed behavior that is affected by so many parameters.
Yeah. Well, I have one finding where I built up a channel map like this from a place that like I said before, this is lab data, but I did take a look at one of the sites that was having issues with Bluetooth performance, and it was very strange because everything was fine for the first 40 minutes, and the channels were actually pretty good. And then I have no idea what happened in the environment, but the last 20 minutes, almost all the channels were really struggling. When Bluetooth has a limit on the number of channels you can map out, you're required to keep at least 20 channels active regardless of the environment. And in this particular case, it was wiped out down to 20 channels, and they were scattered across the spectrum, which indicates that no one of the channels was really any better than the other. So that gives us some basis now for going back to that environment and trying to find out what changed, because apparently something was turned on because it was a very drastic change in the environment. Maybe some piece of equipment was being used that generated noise in this spectrum. We don't know yet, but at least we could see that it was just a really sharp drop off, indicating that there was some event that triggered it.
So in the system you mentioned you have a couple of components that are being monitored. I wonder if you'll see different behavior when you look on data from the two different devices.
Yeah,
Maybe you can
actually,
shed some light.
yeah, actually we do, and I was quite surprised by that too. And we have one piece of equipment that we call a base and one piece of equipment that we call a patient connector, and they both use Bluetooth to an iPad. But one thing that's different about the patient connector is that it's often used for conducting telemetry, as we call it, over low energy Bluetooth to an implant. And so the patient connector has two simultaneous Bluetooth connections, one to a low energy Bluetooth implant and one to the iPad. And so I would expect the performance between those two products to be equivalent when they're operating in the same environment, but it's not. Part of the reason for that, apparently, and this is an area that deserves a little more investigation on our part, but apparently when you're operating this Bluetooth chip in dual mode, the performance of that chip in terms of these channel maps changes when you're using both BLE and Bluetooth Classic at the same time. And it doesn't perform as well because it's trying to struggle with maintaining channels between two different interfaces, whereas the other piece of equipment, the base, just has that one single connection, and it's the same Bluetooth chip and the same firmware behind it, but it just gets better results in the same environment. So that was a surprise.
So you can actually get more insights about how the hardware itself functions that maybe no one else has that, even the company that built the hardware itself, the chips itself.
Yep.
That's impressive.
Well, and so that's a really good point there. That ability to compare is incredibly useful because we can compare between different pieces of equipment. But what it also allows us to do is to compare between performance before and after a firmware change. Like we just recently did a release where we contracted to have the Bluetooth stack modified to improve performance, and we fielded that now. And I'm looking forward to seeing the data from that. to compare to how things performed before that change. So this is a way of getting concrete feedback from the field as to what kind of impact your changes are making.
Definitely. Do you think this method of work is applicable on other short-range communication protocols?
I would think so. I think some of this is going to depend on the technology and what kind of data is available. And in embedded systems, that's going to be part of the trick of observability, is trying to figure out what parts of the system can provide data that you can leverage to learn about this. Like, for example, if a Bluetooth developer doesn't know about the ability to read the channel maps from the implant, you won't get this data. So depending on what kind of interfaces you have and what kind of data you can get from it, you'll have to do some digging to figure out what are the most useful parameters for characterizing the performance. And that was an interesting exercise in all this too. A lot of this was originally just exploratory. Well, let's see what happens if we monitor this.
Another very interesting topic, I think, for many device manufacturers is battery, right? So it's so precious for the device to remain functioning, that had to have a battery that is sufficient for its use, right? So I wonder, what kind of benefits do you see from battery monitoring?
Right. This may not sound like a particularly major issue to people, but as an example, we have some home monitors where one of the components in the home monitor has a rechargeable battery. And if you know anything about rechargeable batteries, they have a lifespan. And the more often you recharge them, the less the full charge capacity you get. And eventually, over time, their capacity is so compromised that the system really can't hold a charge for a reasonable amount of time. So we have one product in the field that there's millions of these. Literally, there's over 1 million products in the field that has a lithium ion battery in it, and they had an expected lifetime of about 5 to 10 years. And so once they got close to that 10-year limit, some of the batteries started having failures. Either their capacities were so run down, or the lithium cells themselves had issues, and it started happening at a much higher rate than expected. And so we had an unexpected problem after this product had been out in the field a number of years with the battery failure rate ramping up to a level that was very difficult to manage. And in that product, we had no way of knowing that was coming. And so on the product I worked on here with the same kind of battery in it, I added observability tracing so that we can keep tabs on the health of the battery. And one of the things we want to know, for example, is how much has the full charge capacity depleted over time. We have targeted the battery to provide 3 hours of runtime. And as that full charge capacity drops, that runtime also drops. And our users would prefer to have the battery last all day. We all know what it's like to have a phone that you have to recharge every 3 hours versus every 3 days. And so we put monitoring in there, and we're keeping a close eye now on, of the fleet of these battery powered instruments, how many of them have had their batteries deplete to below 60%, say, of the original capacity. And that's going to give us an early warning on when we might expect to start seeing issues from the field on the performance of these particular units. And so it could give us the opportunity to do advanced planning to triage the issue, maybe proactively replace those units before they become a problem, and manage the situation in a proactive manner rather than reactively.
You can also use metrics, like if you have any temperature sensor, to actually cross-check those metrics and compare it to the battery's depletion rate, right? So you can actually try to see if there is any environmental effect of unexpected one on the performance.
Yes, as a firmware engineer, every now and then you learn something new about how your hardware performs. And one of the things that I was startled by with this full charge capacity measurement that was reported up is I expected that it would be linearly decreasing over time, but we saw variability in it where sometimes the full charge capacity would unexpectedly increase. And I wondered at first if that wasn't indicating some kind of problem with the hardware or some kind of fault in the firmware algorithm. And it turns out that when you dig into a little deeper into the data sheet, they explain that temperature variations and current draw over time can affect short-term that capacity measurement. So it just helped us understand how to condition the data and not worry about upward fluctuations in the capacity.
Do you think that monitoring or carefully observing the battery status can also help you create software that is more battery saving as it runs?
I think so. Well, one of the things that this type of observation has led to, and I'd like to point out that this is a very iterative process. In an embedded system, you take your first stab at what you think is going to be the most useful data. And the idea is to try and have enough data there where you get core information that you know you can act on, but enough additional information so that you can have some chance at being able to answer questions that you haven't thought of yet. And one of the questions we hadn't thought of to implement in our traces was what's the discharge rate over time. We have multiple different ways of using this instrument, using different wireless connections to other devices, and each one of those has a different profile on how rapidly it burns down the battery, but we don't have a good idea on what that is. And so one of the things that we're doing on our next iteration of the firmware is to actually measure during different use cases what the battery capacity is at the beginning and the end of that use case, so we can measure over time what the depletion rate was, and now have a basis for knowing if it's used in this way, this is how fast it's going to use up the battery. And then in turn, we can use that for product design to size the battery capacity appropriately.
So actually you can make a future decision on the future hardware based on this telemetry that you get from this existing equipment.
Yep. And we're in the process of building out a new platform that is a lower power platform that is intended to be a substitute or a replacement for the one that we're talking about here. And this data will help them drive the design of that future product and evaluate the power reduction, the power savings in that new design, so we have a basis of knowing how much better is it.
So it's like doing a retrospective on how everything functions in your existing product and basically creating the next best product that you can based on this information.
Yep. It not only helps you iterate on refining the firmware itself, it also helps you iterate on refining your hardware.
Exactly, which I think one of the hardest parts, because you can barely know what's happening there, right? So you rely on the data sheets, and you might encounter scenarios that were not tested ever with this hardware as well.
Yep. And again, there's a lot of this stuff you can do by analysis too, and you want to do it by analysis, but it's always, I think, a little touchy to assume that your analysis is an accurate reflection of how it's going to perform in the field. And I always feel better having proof in front of me of what it really does, as opposed to what we analyzed it to do.
Mm-hmm. Yeah, I understand. Okay, so we are now in our final slide for today. Before we proceed, I want to summarize a little bit what we talked so far. So we went over a few observability use cases.
right? We talked about battery monitoring, we talked about Bluetooth monitoring, and I think now we can add some additional final use cases that are relevant to really many of companies that manufacture devices.
For example, what is the memory usage of the device? You can actually really understand what is the quality of the software, of the firmware that is running on it. So you can see if you have some untested flows that caused an extensive memory usage that were not detected in the test. You can see also how people interact with your device physically. So if you have some kind of a button or a screen or a combination of buttons, you can actually figure out from the observability and see if those controllers are being used as expected or if there are many issues. If you see, for example, a button being pressed repeatedly, that can indicate that the user does not know what to do or how to control the device. So did you encounter any insights like that when you use the Sternum platform?
Yeah, there have been some really interesting observations that we've gotten out of this data. I'll start with the one that is most disturbing to me as a Bluetooth developer. It's mentioned here that we can track Bluetooth communication qualities and uncover issues in the Bluetooth library or chip module. We have one metric that we're tracking where on the low energy Bluetooth side, we have periodic transmissions between our instrument and an implant that happens every 32 milliseconds. And if you measure the jitter between those, you have another measure of the quality of your communication link. Ideally, that jitter would be zero. And of course, that's not the way it works. And so we developed a trace that would allow us to create a histogram of the different bins of the deltas in the jitter, anywhere between like 5 milliseconds and 70 milliseconds when the expected jitter is zero. And so you can monitor that over time as well. And it's a different view of how the system is performing than the channel maps. And I saw something very unexpected in the lab when we were doing our anechoic testing, where there was an expected pattern to the jitter where it broadens as noise is introduced into the environment because a periodic transmission will have to be retransmitted when there's noise, and that increases the jitter. And then that means the distance between that transmission and the next one will be shorter because you spent some of that periodic time doing retransmissions. So you see the jitter curve start to flatten out as noise increases. And what we saw is that it would do that and it would look pretty reasonable, but all of a sudden it inverted where there was no change in the environment, no change in the data stream, and all of a sudden we had extreme jitter alternating with really short intervals because those long delays would queue up the data and then there would be zero delays between them. That kind of behavior shouldn't have happened. And so there's something in the algorithm there on how it's servicing the low energy Bluetooth that goes off into some kind of state that recovers once the connection is dropped and recreated. So that's an area of investigation that would help us improve the quality of the performance of our product in the field. But so that's one of my favorite examples that matters a lot to me because these are really hard problems to get insight into. Some of the other more interesting things though is we hear complaints from the field sometimes about the battery discharging while it's being used and shutting itself down. And we wonder, well, how often does that really happen? So we instrumented the code and we can monitor that. We can see how often while they're using it, it loses power. And it turns out that it's like 0.01% of the time. So that's very useful information because if it was 10% of the time, that would be a lot different. And then we didn't need to take a closer look at how we're managing the battery and the battery capacity. So that seems to be a reasonable rate of occurrence. Another thing with the memory usage that can be really useful to embedded developers is in our RTOS environment, we have stack for every task, and those stacks are a fixed size. And during development, you have to ensure that that stack is big enough to handle the worst case utilization of anything that that task is responsible for. And so what we try and do is aim for a reserve of 20%, that we want to see the maximum utilization of that stack to be 80%. And so we put traces in the system to monitor whenever the utilization goes over 85%. And so we've already gotten feedback on that, where there are some cases where we needed to go back and increase the task stack size. And this is in firmware that we've been using for over 5 years, and we never had the observability to see that. And like Lian, you had mentioned, going on to another thing, the button presses are of interest to like our human factors team, because we, like some commercial products I've seen, they try and keep the user interface simple by having like a single multifunction button. And I have an espresso coffee machine that drives me nuts, because there's about a dozen different button press patterns that you need to do to handle error conditions and change different parameters on how the coffee maker works. And you have to have a cheat sheet there. And so we understand that when users use this equipment in the field, how difficult is it for them to keep track of how to use that button? We have 6 different functions assigned to that button that have different functions depending on the context of when it's being used. Like, for example, if you want to turn the unit off, you have to press and hold the button for 5 seconds. So we don't want to allow the user to do that while the product is in use during a patient session, though. So what we do is we monitor how often they try and turn the patient connector off versus how often it actually is able to turn itself off based on use conditions. And there's a big disconnect there. We've seen button press times of 10 and 20 seconds where I'm imagining that somebody's just sitting there mashing on that button, wanting the thing to turn off, and it won't turn off. And so, that type of situation or that type of feedback can help us understand what kind of education and instruction to provide to the field on how to use this product. So it can help us, in short, then get insight into user confusion on our product.
That's amazing. So when we designed the system, we thought about a lot of use cases, and we made a very generic system that could allow you to monitor anything. But the thing that you mentioned, like human factor or thing like that, this is like behind any imagination that the Sternum can provide so much value based on just monitoring how long a button is being pressed and when. So that's amazing.
Yeah, just little simple things like that. You wouldn't think that monitoring a button press could be interesting, but here we are.
Definitely, especially in critical devices, right?
Yeah.
Okay, so our last subject for today is talking more about the security aspect of Sternum. So as we mentioned in the beginning, our offering includes both runtime protection, observability, but also anomaly detection, insights from our cloud platform. And here you can see what kind of benefits you get from this multi-layer security solution. So from one aspect, you can get your IP, intellectual property, protected, because if someone will try to hack the device in order to steal some of the algorithms or the secrets that are used in the device in order for it to function, this runtime protection and also monitoring will actually let you know if someone tries to hack it or to actually debug it with JTAG. So you can get alerted on that, you get tracked on that. And you can also monitor severe behavioral, I would say, anomalies in the device. So in the second example here, we see an anomaly that is being detected on a device that try to interact with an implant over 100 times in a very short amount of time. So this is a clear anomaly that could be performed by someone researching the device and trying to get it into an edge case, for example. And this could be also a performance anomaly, but in the Sternum platform, you can get insights on both.
Yeah, that has helped us during development too, where we had a bug once where there was a situation like that where something wasn't being handled properly and we weren't able to establish a connection, and we were repeatedly trying to get past it, but there was a bug in the way that would prevent it from happening. So, all of a sudden on the dashboard, there's this alert that pops up. So, yeah, that was helpful and it drew attention.
So we are done for today. Wanted to thank you all for joining and watching us, and especially thank you, Chas, for sharing us your time and your insights. That's really, I think, so valuable. I think many people here for sure learned something new.
I was just going to say, well, thank you for inviting me, Lian. It was a pleasure.
Of course. If you have any questions, that's the time. Thank you.
Okay, see, we got our first question here. Chaz, I think this one is for you. Did you see any value from the active runtime protection?
Yes, there's two sources of value from it, in my opinion. One is it's really nice to know that our devices are not being hacked in the field, and so not seeing alerts is good. But we, on the flip side of that, is we do every now and then see some alerts that happen during development because the runtime protection catches some common programming errors like buffer overflows. Every now and then you might write some code that writes past the end of a buffer, and we've had Sternum catch those and bring them to our attention. They ended up not having any impact on the runtime for the cases that we found, so we never would have known that. And with that kind of thing, if you start moving code around and data around, eventually you're going to have an overflow that does cause problems. So that was very helpful.
Thank you. Okay, the next question is also for you. You mentioned you've been collecting data for about a year now. I was wondering how long it took to get some insights from the data.
So it ends up being a pretty straightforward, simple process. Once we deployed our systems, it took very little to integrate Sternum into the system. So the actual investment and development time for us was really more about figuring out what data we wanted to send up for observation. And once it was deployed, it was my first time looking at this kind of data coming in. So it probably took a couple months of getting fully oriented on how the dashboard works, how the queries work, and looking at the data, making sense of it, looking back at the code and seeing where the data came from to double check what it really means. But that's, in my opinion, pretty low overhead for the value that we get out of it. So I'm really thrilled at what a short path it was.
Okay. Another question is, what is the false positive rate for the security platform? That's one for me. So the way that the security mechanism work, as mentioned before, it's by inserting self-verification code throughout the firmware, and the algorithms that actually make sure the device integrity remain as expected are deterministic, meaning that if we detect a violation, it means that there is no false positive. If we detect a violation, that means that something bad has happened. For example, we have many security layers, but one of the layers is detecting memory corruption. So if your memory was corrupted, there's no false positive there. It has been for sure corrupted, and the device is now is in unknown state. Okay, another question. Given the uncertainties you discussed around the Bluetooth in hospital, what are the obstacles for Class 3 devices using Bluetooth in mission-critical tasks?
So I'll take that one. The major challenge and uncertainty is around the wide range of variability that you can get in different operating environments. It appears that hospitals have a lot more Wi-Fi interference, so they're a little bit more challenging to work in. And what that leads us to do then is to look at what are the parameters we can tweak to improve the quality of the product and the quality of that communication, either by adjusting transmit power levels. In some cases, that would make a difference. And also with the new Bluetooth 5 specification, there are different transmission methods that allow lower data rates but higher error correction capabilities. So things like that will help perform improvements too. But yeah, it's very difficult if you depend entirely on Bluetooth to have certainty that all the environments are going to be manageable. So that also leads to a design criteria for having a backup for when Bluetooth is too stressed.
Okay, let's wait a couple of more seconds for any additional question. Okay. I think so that since there are no more other questions, I think we can finalize this webinar for today. I want to thank you all for joining us. Thank you, Chas, and everyone have a great rest of the day.
Thank you, Lian. It was a pleasure, and thank you everyone for attending.